A special example of oscillatory motion is simple harmonic motion. And for these notes, we're going to define and give examples of simple harmonic motion. We're going to talk about what a mass on a spring does, a pendulum swinging back and forth. We're also going to talk a little bit about energy in simple harmonic oscillators with an example problem. So let's start off and talk about what simple harmonic motion is. It's defined as oscillatory motion that can be described by Hooke's law. So that means that it's going to have a restoring force and that the displacement of whatever the object is that's in oscillatory motion is proportional to that force. And so what we need to do is kind of think about the mass on a spring situation. So we have a mass and it's stretched out to its maximum displacement, and it's just sitting there on that spring. So right now, it's got no velocity, and if you let go of it, the restoring force pulls the spring towards the wall, and when it'll pass through the equilibrium position, that relaxed spot where the spring would be if nothing was happening to it, and at that point the velocity is maximum, but it keeps going. It's going to move towards the wall for a distance equal to whatever it was stretched. When it gets fully compressed, it stops again, and then it's going to head back out to the stretched position, passing through equilibrium. And when it gets back out to its fully stretched position, that's one oscillation. When we're talking about the oscillations, we need to talk a little bit about some of the quantities. And one of those is amplitude. And that's just the size of the maximum displacement. That's how far the mass moves from the equilibrium position. It's going to be equal on either side of that equilibrium point. So however far it stretches, that's going to be the same amount that it compresses. It's related to the energy that you put into the spring. It's also independent of period and frequency. So it's not going to change the period and frequency. Energy won't matter to those two quantities. It's measured in meters when you're talking about springs and pendulums. So we talk about the amplitude being independent of period and frequency. And where you might be most familiar with this is a musical instrument, a stringed instrument. So you can pluck the string softly or strongly, loudly, and it doesn't change the note. If you have that same note, you haven't changed the position of your fingers any, but it does change how loud the music is. So you haven't changed the frequency, but you've changed the energy. Another quantity that's important for simple harmonic motion is the period, and that's the amount of time it takes to make one oscillation. It's related to how stiff the system is, and it depends on the mass of the system. So T is the period in seconds, and M is the mass that's hanging from the spring. K is going to be the spring constant again, or the force constant in newtons per meter. And you have the equation, the period is equal to 2 pi times the square root of the mass divided by the spring constant. And it should make sense that the harder something is to make it oscillate, the smaller the period will be, and the faster it's going to vibrate. And a larger mass will cause a larger period, or a longer period. So here's an example. We've got a 5 kilogram mass hanging from a spring. It's going to cause it to oscillate, has a period of 1.5 seconds, and our question is, how much mass do you have to add to change the period to 2 seconds? So first thing we need to do is find out what the force constant is of the spring. So we know the mass is 5 kilograms and the period is 1.5 seconds. We can rearrange our equation or plug it straight in. I went through and did a rearrange on it and plugged it into the equation, and I got that my force constant is 87.7 newtons per meter. Now that I know what the spring force constant is, I can find how much mass it takes to change the period to 2 seconds. And it's that same equation rearranged for mass, because we're still talking about simple harmonic motion of a spring. You plug all those numbers in and you get 8.8 kilograms. So another example of simple harmonic motion is a pendulum, and the pendulum's got even a tighter definition. The angle needs to be less than 15 degrees from the equilibrium point for it to be simple harmonic motion. The expression for this looks very much like the spring. It's going to be the period is 2 pi times the square root of L over G, where L is the length of the string of the pendulum, G is the acceleration due to gravity, and the restoring force is still proportional to the displacement as long as you stay within that small angle. And notice in this case that the mass hanging from the pendulum has no effect. It's just acceleration due to gravity and length. Here's an example. We have a tire swing. Put a kid on the tire swing. We're going to count how many swings they take. So 5 swings. We time it. It's 18 seconds. And we want to know what the length of the rope on the tire swing is. So first thing we do is find the period. And so that's the amount of time for one swing. And we find that that's 3.6 seconds. And then we'll use that and the equation for the period of a pendulum to find the length. Do a quick rearrange and plug things in, and you get 3.2 meters is the length of the string. Now things are moving, so we're going to talk a little tiny bit about energy in a spring. You're going to have kinetic energy and elastic potential energy, and the sum of those is going to be a constant. So we have 1/2 mv squared for kinetic energy and 1/2 kx squared for the elastic potential is always going to be some number. And notice that you think back to the beginning where we talked about the motion of the spring, and we had the where the speeds where it's at 0 at the endpoints and it's maximum in the middle. We can talk a little bit about how this works with the energy. You've got it fully stretched to begin with, and so it's all potential energy and the velocity is 0. Now you let go of it and it's going to swing back through its equilibrium point. At equilibrium point, there's no more potential energy because the spring is fully relaxed, but it's all kinetic. The velocity is maximum. And then it compresses more towards the wall. It's going to store up more energy, and it's going to transfer that kinetic energy to potential until it's fully compressed. And it's going to go back through the equilibrium point where velocity is going to be max again, and then stretch back out again where it's fully stretched and the velocity is 0 and the potential energy is maximum. So potential energy is maximum when it's fully stretched and fully compressed, and the kinetic energy is maximum when it's in the middle at its equilibrium point. So if we want to look at what's the maximum speed of the mass during an oscillation, we have a spring with a force constant of 1200 newtons per meter. It's oscillating with an amplitude of 20 centimeters when you hang it at 0.8 kilogram mass on the spring. And once again, the question is, what's the maximum speed of the mass during the oscillation? So we know that the maximum potential is going to be equal to the maximum kinetic energy. We know our mass, our spring constant, and we know how far the spring is stretched. Remember, that needs to be in meters, so watch those units. And so we just plug things in. We plug in the 1/2 kx squared, set that equal to 1/2 mv squared. Do the math, and you end up with the maximum velocity is 7.7 meters per second. Alrighty, bye-bye.